When you imagine the universe, you likely don't see it as a smooth, uniform expanse. After all, a dense object like planet Earth is vastly different from the void of empty space. However, on the largest scales, the universe is quite smooth, and in its early stages, it was smooth even on smaller scales. Despite the inherently quantum nature of our universe, complete with all the associated quantum fluctuations, you might wonder if it could have started off perfectly smooth and then evolved from there. Let's examine the universe we observe today to find out. On nearby scales, we encounter dense clusters of matter such as stars, planets, moons, asteroids, and even humans. Between these objects lie vast expanses of empty space, interspersed with more diffuse matter like interstellar gas, dust, and plasma. These diffuse clumps either come from dead and dying stars or represent the future sites of stars yet to be born. All of these elements are bound together within our majestic galaxy, the Milky Way. On larger scales, galaxies may exist in isolation as field galaxies, be grouped together in small clusters of just a few, like our own local group, or form larger clusters containing hundreds or even thousands of galaxies. Looking at even grander scales, we observe that these clusters and groups are arranged along vast filaments, some stretching billions of light-years across the cosmos. Between these filaments lie enormous voids, under dense regions with few or even no galaxies and stars. However, when we examine the universe on even larger scales, tens of billions of light-years across, we discover that any given region of space resembles any other. These regions have the same density, temperature, number of stars and galaxies, and types of galaxies. On the grandest scales, no part of the universe is more or less special than any other. Everywhere we look, different regions of space exhibit the same general properties. However, our universe didn't begin with these enormous clumps and voids. When we examine the earliest baby picture of our universe, the cosmic microwave background, we find that the density of the young universe was uniformly distributed on all scales. And when I say uniformly, I mean we measured temperatures of 3K in all directions, then 2.7K, then 2.73K, and finally 2.725K. It was remarkably uniform everywhere. It wasn't until the 1990s that we discovered some regions were just slightly denser and others slightly less dense than average, by about 80 to 90 microkelvin. In its early days, the universe was extremely uniform, with deviations from perfect uniformity being only around 0.003%. This picture from the Planck satellite reveals the deviations from perfect uniformity. The red, hot spots indicate under-dense regions, while the blue, cold spots represent over-dense areas, those destined to evolve into star and galaxy-rich regions. These imperfections, these slight over-densities and under-densities, were essential for the formation of any structure in the universe. If the universe were perfectly uniform, no region would attract more matter than any other, preventing any gravitational growth over time. However, with even those tiny imperfections, just a few parts in 100,000 that our universe started with, after 50 to 100 million years, the first stars had formed. After a few 100 million years, the first galaxies emerged. By a little over 500 million years, so many stars and galaxies had formed that visible light could travel freely throughout the universe, unobstructed by neutral matter. After billions of years, we see the clumps and clusters of galaxies that we recognize today. So, is it possible to create a universe without fluctuations? One that starts perfectly smooth, but develops these fluctuations over time? The answer is no, not if the universe is created in the same manner as ours. Our observable universe emerged from the hot Big Bang, filling space with a hot, dense mix of matter, antimatter, and radiation. The energy for the hot Big Bang originated from the end of inflation, a process where the energy inherent to space itself was transformed into matter and radiation during cosmic reheating. However, the universe doesn't heat up uniformly everywhere because, during inflation, quantum fluctuations stretched across the universe. These fluctuations are the origin of the overdense and underdense regions we observe. If you have a matter and radiation-rich universe with an inflationary origin and the known laws of physics, you will inevitably have fluctuations leading to over-dense and under-dense regions. But what determined their magnitude? Could they have been smaller? The answer is yes. If inflation had occurred at lower energy scales, or if the inflationary potential had different properties, these fluctuations could have been significantly smaller. They could have been 10 times smaller, or even 100, 1,000, 1,000,000, or 1,000,000,000 times smaller than the ones we observe. This is critically important because cosmic structure formation takes a long time. In our universe, it takes hundreds of thousands of years for the initial fluctuations to become measurable as the cosmic microwave background, CMB. From the CMB to the formation of the first stars, it takes around 100 million years. However, transitioning from those first stars to a dark energy-dominated universe, where no new structures form unless already gravitationally bound, is not such a big leap. About 7.8 billion years after the Big Bang, the universe began accelerating. If the initial fluctuations had been much smaller, delaying the formation of the first stars until, say, 10 billion years after the Big Bang, the combination of small fluctuations and dark energy would have ensured that stars never formed at all. How small would those fluctuations need to have been? Surprisingly, only a few hundred times smaller than the ones we actually have. If the scale of these fluctuations in the CMB, shown below, had values around a dozen instead of a few thousand, our universe would have been fortunate to have even one star or galaxy by now, and would certainly look nothing like the universe we see today. If it weren't for dark energy, if we only had matter and radiation, given enough time, structures could form in the universe regardless of how small the initial fluctuations were. However, the inevitability of accelerated expansion creates a sense of urgency, making it crucial that the mean fluctuations are at least about 0.00001% of the average density to have any notable bound structures. If the fluctuations were smaller than that, the universe would have no significant structures at all. But with fluctuations elevated to a massive 0.003% level, we end up with a universe that looks just like ours. Our universe must have started with lumps, but if inflation had been different, the size of those lumps would have varied significantly. If the lumps were much smaller, there would be no structure at all. If they were much larger, the universe could have been catastrophically filled with black holes from a very early time. Creating the universe we have today required an exceptionally fortunate combination of circumstances, and fortunately for us, the result appears to be just right. Thank you for joining me on this cosmic exploration. Don't forget to like, share, and subscribe for more mind-bending content. Until next time, stay curious and keep looking up.